Hello, and thank you for joining me on this galactic journey. Tonight, we will slowly drift into the earliest moments of the universe, back to a time before stars, before light, before time itself. Imagine a vast stillness, a space without edges, where everything that would ever exist is waiting quietly to be born. As you breathe slowly, picture the first faint sparks of creation, tiny ripples in the fabric of space and time, expanding outward, filling emptiness with possibility. Feel the subtle pulse of the universe's beginnings, the gentle unfolding of matter and energy as protons, neutrons, and electrons emerge. Let your mind wander through cosmic inflation, the cooling and settling of fundamental particles, and the first gentle glow of light traveling freely through space. Allow yourself to float among the earliest stars, forming from drifting clouds of hydrogen, guided by invisible forces shaping the galaxies. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. Before there was anything to measure, before light could stretch across space or time could mark its passage, there was only a profound stillness, an emptiness that defies ordinary thought. In this infinite quiet, there were no stars, no galaxies, no planets. Space as we perceive it did not exist, and the concept of time held no meaning. Scientists speak of this epoch as pre-Big Bang, a period that stretches the limits of human imagination. It is here, in this primordial quiet, that we must gently acknowledge a truth. While multiple ideas exist about how the universe began, the model with the most observational support is the Big Bang, even though it has not been proven beyond all doubt. Other hypotheses, from quantum cosmology to the possibility of a multiverse, offer intriguing visions of cosmic beginnings. Yet the Big Bang remains the framework that aligns most consistently with the evidence we observe today. We imagine the universe compressed into an inconceivably small point, a singularity where density, temperature, and energy converge beyond comprehension. Within this infinitesimal seed, every particle, every force, every potential structure was bound together in perfect, unimaginable unity. Modern cosmology allows us to peer backward, tracing the faint traces of this origin through mathematics and observation. Though these ideas are abstract, they invite a serene contemplation of existence itself, a meditation on the very conditions that made everything possible. The notion of nothingness stretches beyond human perception. It is not empty in the way a room is empty, nor dark as a shadowed forest. It is a profound absence, a stage upon which the universe had yet to perform its first act. Yet, within this absence, there is a subtle suggestion of potential, a latent energy, imperceptible but pregnant with possibility. Quantum cosmology hints at fluctuations within this void, tiny blips in a field of potential that might, in time, ignite the cosmos. Some scientists propose that our universe is but one of many in a vast multiverse, each emerging from its own moment of creation, each invisible to the others, except in theory. As we consider these early moments, we are drawn to a mental landscape of primordial density fluctuations, like ripples frozen in a liquid that has yet to exist. These faint stirrings are almost imperceptible, yet they hold the seeds of every galaxy, every star, and every planet that will eventually follow. Abstract visualizations depict energy fields pulsing softly in the darkness, each one a whisper of what is to come. This is a time before light, before sound, where the universe is an elegant enigma, waiting for the first spark that will set its narrative in motion. Time itself emerges, gradually from this stillness, entwined with space in a delicate, inseparable bond. The laws of physics, as we understand them, begin to take shape, providing a framework for matter and energy to interact. The very fabric of existence stretches outward from this initial point, a gentle unfolding that will eventually sculpt the cosmos. In this nascent environment, the first inklings of order appear, tiny perturbations that will one day guide the formation of stars and galaxies. Though invisible to the eye, these formative structures set a calm rhythm for the universe's eventual growth. The mind can wander in this prelude, imagining a space that is simultaneously infinite and infinitesimal, dark yet brimming with latent energy. It is a meditation on the origin of the universe, a reflective journey through the earliest chapters of cosmology. As we explore the boundaries of nothingness, we also explore the limitations of human understanding. These concepts invite contemplation rather than certainty, a gentle encouragement to marvel at what lies beyond our perception. In this silent, formless expanse, we begin to feel the first stirrings of what will become the cosmos, potential energy gathering, fluctuations in the fabric of reality, and the imperceptible hints of time and space coalescing. The stage is set for creation, a tranquil anticipation before the first burst of light and matter reshapes the void into the universe we are only beginning to understand. Even within this stillness, there is a suggestion of movement, a soft, inevitable unfolding that will carry the universe from nothingness into being. As we linger in this moment, we prepare to witness the delicate birth of time, the first quiver of energy, and the faint glimmer of a cosmos waiting to awaken. In an instant beyond comprehension, the universe surged into existence. Time, space, and energy unfurled together, forming the stage upon which the cosmos would evolve. This awakening begins at the Planck Epoch, a moment so extreme that our current understanding of physics can only hint at its nature. Gravity, electromagnetism, and the nuclear forces had not yet fully separated, entwined in a searing, turbulent unity. Energy densities were immense, and the fabric of space itself trembled with nascent potential. From this primordial point, space expanded with extraordinary rapidity in a period known as cosmic inflation. Distances multiplied faster than light could traverse them, stretching minuscule quantum fluctuations into macroscopic imprints that would later guide the formation of galaxies. This expansion was not a movement through space, but an expansion of space itself, stretching the very grid of existence. Tiny variations in energy, once microscopic, were amplified to become the skeleton of cosmic structure. Matter had not yet cooled into familiar forms. Instead, the universe was a dense, radiant soup of energy, with particles flickering in and out of existence in accordance with quantum rules. Photons, electrons, and quarks coexisted in an incandescent haze, colliding and exchanging energy in a perpetual, gentle agitation that carried the first hints of order. Even in this extreme environment, the universe followed precise mathematical laws, allowing patterns to emerge from apparent chaos. Gravity, although still indistinct from the other forces, began its subtle shaping influence. Regions with slightly higher energy density exerted a minuscule pull, drawing in surrounding matter and creating the first seeds of structure. These fluctuations, imperceptible at the time, would expand over billions of years into the vast galaxies and clusters that now punctuate the cosmos. Observing these primordial ripples in the cosmic microwave background allows scientists today to trace the earliest moments of this unfolding story. As inflation slowed, the universe transitioned into a state where the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, assumed the distinct roles familiar to modern physics. Space remained extremely hot and dense, yet expansion continued, gradually lowering temperatures to a level where particle formation could take hold. Quarks combined to form protons and neutrons, though collisions remained energetic enough to prevent stable atomic nuclei from forming just yet. The earliest photons were trapped in this turbulent plasma, scattering endlessly off-charged particles. Light could not yet traverse space freely, yet its presence hints at the structure of the emerging cosmos. This era, dominated by radiation and energy, set the stage for the first moments when matter would begin to dominate, paving the way for atoms, stars, and galaxies to follow. Inflation left behind subtle imprints, minuscule variations in density that are detectable today as faint temperature differences in the cosmic microwave background. These differences reveal the universe's initial conditions, acting as a cosmic fingerprint of the Big Bang's first heartbeat. Observations of these ancient signals confirm the remarkable uniformity and simultaneous expansion of the universe, providing a window into events that occurred almost 14 billion years ago. Throughout this expansion, the interplay between energy, matter, and the fundamental forces dictated the universe's evolution. Regions that were slightly denser than their surroundings grew more pronounced, while underdense regions became vast cosmic voids. This delicate balance, guided by gravity and the early distribution of energy, would sculpt the large-scale structure of the universe over billions of years. Visualizing this moment evokes a serene yet awe-inspiring tableau, a boundless sea of luminous energy rippling through space, the first gentle undulations in a vast cosmic fabric, and the earliest whispers of matter beginning to take form. Although invisible to the human eye, this initial expansion contains the blueprint for everything that follows: galaxies, stars, planets, and the intricate cosmic web connecting them. By tracing these origins, we recognize that the universe's earliest instants were not chaotic, but meticulously orchestrated by natural laws. Every fundamental interaction, every fluctuation, and every burst of energy contributed to the architecture we observe today. In this nascent universe, the stage was set for matter and light to emerge, laying the foundation for the first atoms, the first stars, and the slow, inexorable unfolding of cosmic history. The universe, once an unfathomable energy field, began to cool, allowing the first fundamental particles to emerge. In this embryonic epoch, protons and neutrons coalesced from free quarks, forming the primary building blocks of matter. Electrons, lighter and more agile, moved freely through the searing energy sea, interacting with these nascent nuclei in a continuous exchange that shaped the earliest matter. The interactions were governed by the fundamental forces, establishing the patterns that would guide all subsequent cosmic development. During the first few minutes, conditions permitted a delicate balance known as nucleosynthesis. Hydrogen and helium nuclei formed from the merging of protons and neutrons, while trace amounts of lithium appeared in the background. These early elements, sparse yet crucial, laid the groundwork for the future chemical complexity of the cosmos. The relative abundance of hydrogen and helium remains remarkably consistent, a testament to the precision of these formative moments, and a relic detectable in the interstellar medium today. Photons, once trapped by constant collisions with charged particles, began to find room to travel as the universe expanded and cooled further. This liberation of light, known as recombination, occurred roughly 380,000 years after the Big Bang. Electrons bound with nuclei to form neutral atoms, creating a transparent medium through which radiation could pass unimpeded. The cosmic microwave background, a faint relic of this epoch, preserves an image of the early universe in gentle ripples of energy, providing scientists with a map of conditions nearly 14 billion years ago. The emergence of these first photons was not sudden in the way a flame bursts into life, but a gradual unveiling as the density of matter decreased enough to permit light to move freely. The spectrum of this radiation, uniform yet subtly varied, carries within it the fingerprints of the initial density fluctuations that seeded galaxies. By studying this ancient light, astronomers can reconstruct the universe's infancy, tracing the scaffolding from which cosmic structures would arise. As the universe continued to expand, regions with slightly higher concentrations of matter began to exert gravitational influence over their surroundings. Though still diffuse, these variations formed the preliminary shapes of the cosmic web. The interplay between matter and radiation shaped the evolution of the cosmos, determining which regions would become the future hosts of galaxies and which would remain voids. This early alignment of forces established the delicate architecture observed in large-scale surveys of the modern universe. The first photons also carried information about temperature, density, and composition, a cosmic record of the conditions prevailing during recombination. These ancient signals illuminate the early universe in a serene and persistent glow, revealing both uniformity and subtle irregularities. The faint anisotropies encoded in this light hint at the structures that would later condense into the first stars and galaxies, linking the era of particle formation directly to the birth of celestial bodies. In the cooling cosmos, hydrogen remained the dominant element, its simplicity a foundation for future fusion reactions. Helium, though less abundant, contributed to the chemical diversity necessary for the emergence of complex matter. The energy carried by photons permeated space, maintaining a dynamic equilibrium that influenced how matter would collect into denser regions. Over millions of years, these interactions guided the first steps toward cosmic organization, allowing gravity to shape clouds of gas into potential stellar nurseries. Observing this era is like peering through a delicate veil stretched across billions of years. The patterns present in the cosmic microwave background reveal the universe's earliest blueprint, capturing the interplay between light and matter in a frozen tableau. Each fluctuation, each subtle variation, echoes the initial conditions set by inflation, illustrating how a universe born from a singular energy field transitioned into a cosmos of matter and radiation. From this stage, the universe was no longer a uniform glow, but a canvas of potential. The interactions between particles and photons, guided by the laws of physics, set the tone for the formation of atoms, stars, and galaxies. The gentle illumination of the cosmic microwave background persists as a reminder that light was born alongside matter, and that even in its infancy, the universe carried the promise of structure, complexity, and an unfolding story yet to be fully revealed. Gravity began its patient work in the cooling universe, drawing tenuous clouds of hydrogen and helium into regions of slightly higher density. Over millions of years, these clouds grew heavier, compressing under their own weight. Within the densest cores, the pressure and temperature increased enough to ignite nuclear fusion, sparking the birth of the first stars. These early stellar furnaces transformed the cosmos, bringing light to a universe that had been dark since recombination. The initial stars, known as Population 3 stars, were enormous and short-lived. Formed almost entirely from hydrogen and helium, they lacked the heavier elements present in later generations. Their immense mass caused nuclear fusion to occur at a ferocious rate, emitting powerful radiation that began to ionize surrounding gas. This reionization marked the universe's first large-scale illumination, creating luminous pockets within the otherwise dark expanse and allowing photons to travel further than before. Dark matter played a silent yet essential role in this cosmic awakening. Invisible to telescopes, it exerted gravitational influence across vast regions, guiding gas into the densest regions where stars could ignite. The interplay between ordinary matter and dark matter dictated where these first stellar nurseries emerged, shaping the early architecture of the cosmos. Although unseen, this scaffolding provided a framework that influenced galaxy formation for billions of years to come. As hydrogen fused into helium in stellar cores, the stars released enormous amounts of energy, radiating light across the surrounding space. Stellar winds carried newly formed elements into the interstellar medium, enriching it with the first traces of carbon, oxygen, and nitrogen. These heavy elements, absent in the earliest particles, became the seeds for future generations of stars and planets. Through this enrichment, the universe gradually acquired the chemical diversity necessary for complex structures and, much later, life itself. Clusters of these first stars began to group into nascent galaxies. Gravity continued to pull matter together, forming loose assemblies that would eventually evolve into spiraling or irregular galaxies. Each new generation of stars contributed energy and elements to their environments, subtly reshaping the surrounding gas and guiding further star formation. This iterative growth set the pattern for the hierarchical structure of the cosmos, establishing regions of dense illumination amid vast cosmic voids. The radiation from these primordial stars had profound effects on their environment. It heated interstellar gas, influenced the formation of subsequent stars, and drove the gradual reionization of the universe. Observing this era today, astronomers detect faint signatures of ancient light, including absorption lines in distant quasars and subtle variations in the cosmic microwave background. These measurements provide insight into the timing and extent of the first luminous events, offering a glimpse into the universe's earliest stellar ecosystems. Visualizing these first stars evokes a sense of emergence from darkness. Dense clouds collapse into brilliant points of light, flickering against the deep backdrop of space. Nebulae, energized by ultraviolet radiation, glow with diffuse intensity, painting the cosmos with the first colors beyond pure hydrogen and helium. This early illumination set a rhythm for cosmic evolution, establishing the interplay between gravity, radiation, and matter that would guide the universe for billions of years. By tracing the emergence of these initial stars, it becomes clear how fundamental forces sculpted the young universe. Gravity concentrated gas, nuclear fusion released energy, and radiation shaped subsequent generations of stars. The enrichment of the interstellar medium laid the groundwork for planetary formation, while the assembly of proto-galaxies created the first hints of large-scale cosmic structure. Each luminous burst, each subtle interaction contributed to a universe that was evolving toward complexity, order, and observable beauty. The era of first light marked both an end and a beginning. Darkness receded as the first stars illuminated the void. Yet this illumination revealed new possibilities for matter to gather, for galaxies to form, and for cosmic webs to extend. In this delicate balance between radiation and gravity, the universe matured from simple clouds of gas into a dynamic landscape where stars and galaxies would flourish, establishing a foundation for the intricate cosmos we observe today. Billions of years after the first stars ignited, the universe had grown into a complex tapestry of galaxies, clusters, and cosmic voids. Observing this vast expanse, scientists discovered that its structure retains a memory of the earliest fluctuations in density, frozen into the very fabric of space. By tracing these patterns, researchers can reconstruct the universe's development, revealing a record of its infancy, written in light, matter, and motion. The cosmic microwave background serves as a primary tool for this investigation. This faint radiation, emitted during recombination, carries subtle temperature variations that reflect the uneven distribution of matter in the young universe. By mapping these variations with high precision, astronomers can identify regions that would later evolve into galaxies and clusters. The contours and ripples in this radiation provide a window into conditions just 380,000 years after the Big Bang, offering a direct link to the primordial universe. Galaxies themselves serve as tracers of cosmic history. Large-scale surveys map the distribution of these luminous islands across billions of light-years, revealing a web-like pattern that mirrors the initial density fluctuations. Interconnected filaments of galaxies thread through vast voids, forming a skeleton of matter that outlines the influence of dark matter. These structures, though invisible to the eye, govern the formation and motion of luminous matter, guiding the universe's large-scale evolution. Redshift measurements allow astronomers to track the expansion of space. Light from distant galaxies is stretched to longer wavelengths as it travels, providing insight into both distance and velocity. By cataloging these shifts, researchers construct three-dimensional maps of the cosmos, revealing how matter has clustered and moved over billions of years. These observations confirm that the universe is expanding, and they illuminate how early conditions shaped the present arrangement of galaxies and voids. Spectroscopy enhances this exploration, allowing scientists to decode the composition and motion of celestial objects. By analyzing the light emitted or absorbed by galaxies and interstellar gas, researchers determine chemical abundances, temperature, and density. These details reveal how early star formation enriched the universe with heavy elements, influencing the evolution of subsequent generations of stars and the potential for planetary systems. Each measurement ties back to the foundational moments of the universe, connecting primordial fluctuations, particle formation, and the first stellar nurseries to the complex cosmos we observe today. Gravitational lensing provides another window into unseen matter. Massive objects bend light from background galaxies, distorting and magnifying their appearance. By studying these effects, scientists map the distribution of dark matter, revealing the invisible scaffolding that shapes the universe on grand scales. This hidden framework confirms that the structures observed in luminous matter are guided by a deeper, unseen influence, extending the continuity between early density fluctuations and present-day cosmic architecture. The interplay between light, matter, and gravity demonstrates the universe's coherent evolution. Even the faintest galaxies contain clues about the primordial environment, while the clustering of matter reflects billions of years of gravitational interaction. By tracing these patterns, astronomers reconstruct a narrative of cosmic growth, observing how the first stars and galaxies influenced their surroundings and how initial conditions dictated the arrangement of matter over immense distances. Visualizations of this era depict vast networks of galaxies stretching across space, their luminous cores punctuating the darkness like distant lanterns. Filaments of dark matter, traced through gravitational effects, connect clusters in intricate webs, showing that the universe's present structure emerges naturally from the fluctuations that originated during inflation. The combination of observational techniques, cosmic background mapping, galaxy surveys, redshift measurement, and lensing analysis creates a detailed and harmonious picture of cosmic history. Through these methods, the universe becomes a map of its own origin, a reflection of the forces and conditions that shaped it from the earliest instants. Patterns observed today correspond directly to events billions of years ago, linking matter, light, and dark matter across vast scales. In studying these ancient signals, scientists gain not only insight into cosmic structure, but also a deeper appreciation of the unfolding story of existence. Tracing a line from the first flickers of matter to the galaxies that now illuminate the cosmos. In the wake of the first stars, matter continued to assemble under the influence of gravity, forming the earliest galaxies. These initial structures were modest in size, irregular collections of stars and gas bound together by the invisible hand of dark matter. Over hundreds of millions of years, these proto-galaxies merged and grew, gradually transforming into the sprawling spirals, ellipticals, and irregular galaxies that populate the cosmos today. The role of dark matter in shaping these early formations cannot be overstated. Though it emits no light, its gravitational influence directed the flow of hydrogen and helium, guiding the assembly of the first galactic structures. Dense concentrations of dark matter acted as anchors, attracting gas clouds that would ignite into stars and clusters. This scaffolding ensured that galaxies were not randomly distributed, but organized along the filaments and nodes of the emerging cosmic web. Within these nascent galaxies, star formation became a cyclical phenomenon. Hydrogen and helium clouds collapsed under gravity, sparking nuclear fusion in the cores of new stars. Massive stars lived briefly, but expelled heavier elements into the interstellar medium when they ended their lives in supernovae. These enriched gases seeded subsequent generations of stars, gradually increasing the chemical complexity of galaxies. The ongoing birth and death of stars transformed the galactic environment, creating regions of intense radiation, expanding nebulae, and the diffuse glow of starlight filling interstellar space. Collisions between proto-galaxies further accelerated their growth and evolution. When gas-rich galaxies merged, gravitational forces compressed material, igniting bursts of star formation. These interactions shaped the morphology of galaxies, sometimes producing spiral arms, sometimes creating irregular or elliptical configurations. Observations of distant galaxies show that such mergers were far more common in the early universe, providing evidence of how large-scale cosmic structures evolved from comparatively small beginnings. The interplay between baryonic matter and dark matter also influenced the distribution of stars within galaxies. Dense central regions became stellar hubs, while less concentrated outskirts formed extended halos of gas and stars. The rotation curves of these galaxies reveal the unseen mass of dark matter, confirming its presence as a dominant component of galactic structure. This hidden framework allowed galaxies to retain their integrity during mergers and interactions, maintaining the continuity of cosmic evolution. Radiation emitted by young, massive stars illuminated their host galaxies, gradually piercing the surrounding intergalactic medium. The cumulative effect of this starlight contributed to the reionization of the universe, marking a transition from neutral gas to an ionized environment. This shift enhanced the transparency of space, allowing light from distant galaxies to travel farther and providing astronomers with a clearer window into cosmic history. Over time, galaxies began to cluster under mutual gravitational attraction. Groups of galaxies coalesced into clusters and superclusters, interconnected along the vast filaments of the cosmic web. Between these clusters, immense voids formed where matter was sparse. This large-scale architecture illustrates the direct link between the tiny fluctuations in density present after inflation and the immense organized structures we observe billions of years later. Visualizing these early galaxies evokes a sense of emergence from the diffuse haze of hydrogen and helium. Spiraling arms of young stars, luminous cores, and glowing nebulae punctuate the darkness of space. Each galaxy contains a story of repeated formation and transformation, a narrative shaped by the accumulation of matter, the influence of dark matter, and the energetic interplay of stellar radiation. These systems are the building blocks of the universe's complexity, creating the environments necessary for planetary systems, star clusters, and the potential for life. By tracing the rise of galaxies, it becomes clear how gravitational attraction, stellar feedback, and chemical enrichment combined to structure the universe. Each filament of the cosmic web, each cluster of stars, is a testament to the initial conditions imprinted during the universe's earliest moments. The cosmos, once a simple distribution of hydrogen and helium, now displays intricate formations that will continue to evolve, carrying the echoes of its origin through the light of countless stars. Beneath the luminous galaxies and radiant nebulae lies an invisible framework that structures the universe, the cosmic web. This vast network of filaments, composed primarily of dark matter, extends across hundreds of millions of light-years, shaping the distribution of visible matter. While galaxies mark the nodes and clusters of this web, the underlying scaffolding of dark matter dictates where stars ignite, how galaxies assemble, and the patterns that emerge across the cosmos. Evidence of dark matter comes from its gravitational influence. Observations reveal that galaxies rotate at speeds inconsistent with the mass of visible stars and gas alone. Without additional, unseen mass, these systems would fly apart. Gravitational lensing further confirms this hidden presence, as light from distant objects bends around massive structures, often in ways that exceed the influence of observable matter. By studying these subtle distortions, astronomers can map the unseen distribution of dark matter, revealing the skeletal structure of the universe. Filaments of the cosmic web stretch between dense galaxy clusters, forming vast corridors through which gas and matter flow. Within these channels, hydrogen and helium stream along gravitational gradients, feeding the growth of galaxies. The intersections of filaments, known as nodes, become regions of intense accumulation where galaxy clusters and superclusters form. This organization reflects patterns seeded in the universe's earliest moments, when slight density variations from inflation expanded into the macroscopic structures we observe today. The interplay between luminous matter and dark matter governs the evolution of galactic environments. Galaxies within filaments often exhibit higher rates of star formation, fueled by the steady inflow of gas. In contrast, isolated galaxies in cosmic voids receive fewer resources, evolving more slowly. This relationship highlights how the invisible web shapes not only the spatial distribution of galaxies, but also their internal dynamics and life cycles. Mapping the cosmic web relies on a combination of observational techniques. Redshift surveys chart the positions and velocities of millions of galaxies, revealing their arrangement across three-dimensional space. Weak gravitational lensing measures the distortion of background light, tracing mass even where no luminous matter is present. These methods, complemented by computer simulations, provide a detailed view of the large-scale structure of the universe, confirming the critical role of dark matter in cosmic architecture. Energy emitted by galaxies interacts with their surroundings, influencing the gas within filaments. Stellar winds, supernovae, and active galactic nuclei inject heat and momentum into the intergalactic medium, regulating star formation and the flow of matter along filaments. These feedback mechanisms demonstrate the dynamic relationship between ordinary matter and the underlying dark matter structure, reinforcing the interdependence that governs cosmic evolution. Visualizations of the cosmic web reveal an intricate, almost ethereal arrangement. Filaments stretch like threads of light through the darkness, connecting luminous clusters while spanning enormous distances. Between these threads lie immense voids, regions with few galaxies and very low matter density. Together, this pattern forms a lattice that organizes the universe on scales far beyond individual galaxies, showing that the cosmos is neither random nor chaotic, but shaped by the combined influence of gravity, dark matter, and the flow of energy. Simulations of cosmic evolution demonstrate how early density fluctuations, amplified by inflation, became the backbone of this web. As matter condensed along these filaments, galaxies emerged at intersections and grew through mergers and accretion. Over billions of years, this structure expanded and evolved, guiding the formation of galaxy clusters, superclusters, and the vast voids between them. Observations of the cosmic microwave background link directly to these patterns, connecting the earliest moments of the universe to its present architecture. By understanding the cosmic web, we gain insight into the forces that sculpted the universe from its infancy. Dark matter, though invisible, organizes the cosmos with an elegance that is revealed only through careful observation and simulation. This hidden framework shapes the journey of galaxies, the flow of intergalactic gas, and the distribution of luminous matter, providing a unifying context for the growth of cosmic structure, from the first stars to the vast expanse we observe today. Every photon traveling through space carries a story. Light emitted by the first stars, the earliest galaxies, and the residual glow of the cosmic microwave background stretches across billions of years, linking past and present. These streams of radiation traverse vast cosmic distances, bent by gravity, absorbed and re-emitted by interstellar matter, yet always preserving a record of the universe's history. From the earliest luminous sources, photons began escaping the dense hydrogen clouds that surrounded them. Young stars emitted ultraviolet radiation that ionized the surrounding gas, gradually transforming their environments. As light propagated outward, it encountered the expanding fabric of space. The expansion stretched its wavelengths, a phenomenon known as redshift, which allows astronomers to measure both distance and the epoch in which the light originated. Each observation acts as a temporal bridge, revealing events that occurred billions of years before Earth even existed. The cosmic microwave background provides the most ancient illumination available to human instruments. Emitted during recombination, it represents the universe's first transparent light, a uniform glow imprinted with subtle fluctuations that correspond to density variations in the early cosmos. Observing this relic allows scientists to reconstruct the primordial conditions that guided galaxy formation and large-scale structure. These faint anisotropies serve as fingerprints of the initial quantum fluctuations, preserved through the intervening eons of cosmic evolution. Galaxies themselves emit light across a broad spectrum. Young massive stars shine predominantly in ultraviolet and visible wavelengths, while older populations radiate in infrared and radio. As this light travels across space, it is influenced by gravitational lensing, bending around massive structures and magnifying distant objects. By measuring these distortions, astronomers can trace the distribution of both luminous and dark matter, unveiling the scaffolding upon which the cosmic web is built. Spectroscopy further enhances our understanding of ancient light. By decomposing the spectrum of starlight or galactic emissions, scientists identify the chemical composition, temperature, and motion of celestial objects. This information reveals the enrichment history of the universe, showing how successive generations of stars synthesized heavier elements and dispersed them into interstellar space. Each spectral line, each absorption feature, is a chronicle of processes that occurred long before planets coalesced or life arose. The interplay of light and expansion also serves as a natural clock. Photons traveling from the earliest galaxies to our telescopes provide a direct measure of cosmic time, allowing the reconstruction of the universe's growth over billions of years. Observing distant galaxies is equivalent to looking back in time, capturing the stages of evolution from star-forming regions to mature galactic structures. In this way, light becomes both messenger and archive, connecting observation with history. As photons navigate intergalactic space, they reveal the geometry and expansion of the cosmos. The degree of redshift indicates the velocity at which galaxies recede, reflecting the influence of dark energy on cosmic growth. Patterns of absorption in intergalactic gas trace the distribution of matter, showing how the universe's structure extends far beyond what is visible to the eye. Every beam of light carries evidence of the forces and events that shaped the cosmos, bridging the epochs between the Big Bang and the present day. Visualizing light across time presents a tableau of continuity. Streams of photons, invisible to human sight, illuminate distant galaxies, interweave through cosmic filaments, and connect the first stars with the complex structures we observe today. This journey is uninterrupted by billions of years, yet it arrives as a faint, measurable signal, allowing humanity to trace the universe's expansion, chemical evolution, and large-scale structure. By following the path of ancient light, scientists gain insight into the universe's history, linking the earliest particles and stars to the formation of galaxies and cosmic clusters. Light not only illuminates space, but also encodes the memory of the cosmos, offering a bridge between the unfathomable past and our present understanding. Through this illumination, the universe narrates its own story, revealing the rhythm of cosmic evolution and the enduring interplay of matter, energy, and time. Space itself stretches, carrying galaxies away from one another in a slow yet relentless motion that has persisted for over 13 billion years. Observations of distant galaxies reveal that their light shifts toward longer wavelengths, a phenomenon known as redshift, indicating that the cosmos is not static but continuously expanding. This expansion is a fundamental feature of the universe, tracing back to the initial moments of the Big Bang and the rapid inflation that followed. The concept of an expanding universe emerged from the observation that galaxies, on average, move away from each other, with more distant galaxies receding faster than those nearby. This relationship, described by Hubble's law, provides a direct measure of cosmic growth and allows astronomers to calculate the universe's scale over time. Expansion does not occur through motion within space, but rather as an enlargement of space itself, stretching the distances between all cosmic structures. Dark energy plays a critical role in the universe's ongoing growth. Although invisible and mysterious, this force appears to counteract the gravitational attraction between galaxies, accelerating expansion across the largest scales. Measurements of supernovae and cosmic background radiation reveal that dark energy dominates the current dynamics of the cosmos, shaping its evolution and influencing its ultimate trajectory. Galaxy clusters provide tangible evidence of this expansion. While gravity pulls galaxies together into bound systems, the space between these clusters continues to grow. Over billions of years, cosmic voids have widened, and filaments of the cosmic web have stretched, creating the large-scale architecture we observe today. This dynamic balance between gravitational attraction and universal expansion defines the structure of the cosmos, determining the distribution of matter and the growth of cosmic networks. Redshift not only indicates expansion, but also functions as a cosmic clock. By measuring the stretching of light from distant galaxies, astronomers determine how long it has traveled, offering insight into the age of celestial objects and the time elapsed since the universe's earliest stages. These measurements allow scientists to reconstruct the evolution of galaxies, clusters, and large-scale structures, tracing a continuum from the initial density fluctuations to the sprawling cosmos we inhabit. Expansion also affects the cosmic microwave background, the residual radiation from the Recombination era. As space stretches, this radiation cools, producing the uniform, faint glow observable today. Tiny fluctuations in the background reveal the imprints of early density variations, and hint at the regions where matter would accumulate to form galaxies and clusters. Through these patterns, the large-scale distribution of matter becomes intimately connected to the universe's expansion history. Visualizing the expanding universe evokes a sense of gradual unfolding. Galaxies drift apart along invisible trajectories, the spaces between them growing with time, while clusters and filaments maintain their cohesion within the cosmic web. This duality illustrates how expansion operates on the grandest scales, subtly reshaping the universe while preserving its internal structure and interconnectedness. By examining the mechanics of expansion, scientists gain insight into both the present state of the universe and its future development. The interplay of gravity, dark energy, and the stretching of space defines the cosmic stage, guiding the evolution of galaxies, clusters, and voids. Observing the universe in motion allows us to witness the unfolding story of space itself, connecting the earliest instance of the Big Bang to the continuing growth and transformation of the cosmos across billions of years. Vast expanses of space stretch beyond the limits of our observation, carrying galaxies, clusters, and filaments whose light may never reach us. The universe extends in every direction, revealing only a portion of its totality, while the remainder remains hidden behind the observable horizon. In this immense canvas, echoes of its earliest moments persist, recorded in the distribution of matter, the patterns of radiation, and the subtle influence of gravity. From the first flickers of energy and matter, the universe has evolved through cycles of star formation, galactic assembly, and chemical enrichment. Photons emitted billions of years ago continue to arrive at Earth, carrying information about conditions that existed in distant epochs. These signals, from the cosmic microwave background to the light of the earliest galaxies, act as a bridge connecting the origins of the cosmos to its current state. Invisible forces, most prominently dark matter and dark energy, shape the architecture of the universe. Dark matter provides the gravitational scaffolding for galaxies and clusters, while dark energy drives the acceleration of cosmic expansion. Together, they govern the growth and arrangement of large-scale structures, dictating both the formation of luminous matter and the evolution of space itself. Observations of gravitational lensing, galactic rotation curves, and supernova provide evidence for these forces, offering insight into the unseen yet fundamental components of the cosmos. The universe retains a memory of its beginnings in its composition and structure. Regions of higher density, seeded by primordial fluctuations, have grown into clusters of galaxies connected by filaments of dark matter. Void spaces, vast and largely empty, separate these structures, creating a cosmic web that mirrors patterns established in the first moments after inflation. By studying this framework, astronomers reconstruct a narrative spanning billions of years, connecting particle formation, star birth, and galactic evolution into a continuous story. Light traveling across these immense distances illuminates not only the matter it encounters, but also the passage of time itself. Every photon carries the imprint of its origin, tracing the conditions of stars, galaxies, and nebulae billions of years ago. Red-shifted wavelengths reveal how the universe has stretched and expanded, while subtle absorption features encode the presence of gas clouds, interstellar dust, and elemental composition along its path. The faint glow of the cosmic microwave background preserves patterns of primordial fluctuations that gave rise to galaxies, clusters, and the large-scale cosmic web. Each signal serves as a message from the past, a record of events so distant and ancient that they challenge our imagination, yet remain accessible through careful observation. By interpreting these signals, scientists reconstruct a detailed chronicle of cosmic history. Light interacts with gas, dust, and gravitational fields, bending and shifting in response to the structures it traverses. Observations of distant galaxies reveal their formation stages, star populations, and chemical enrichment, while absorption lines trace the evolution of intergalactic gas over billions of years. In this way, light functions as both witness and guide, connecting the earliest nuclear reactions in stars to the assembly of vast galactic clusters. Patterns also reveal the influence of invisible forces, including dark matter and dark energy, showing how unseen agents shape the observable universe. In contemplating the universe on such scales, the immensity of existence becomes deeply evident. Every photon forms a link in a continuum, stretching from the emergence of matter and light to the structures we see today. Galaxies, clusters, filaments, and voids are components of a unified cosmic evolution, each influenced by events from the early universe. These echoes of infinity remind us that the cosmos is a dynamic system, shaped by forces both visible and unseen, and that patterns imprinted during its infancy continue to govern structure across billions of years. Even as we probe the most distant reaches, light bridges epochs, revealing not only where the universe has been, but also guiding our understanding of its potential futures. The cosmos carries the memory of its history and offers insight into the complex forces that govern its ongoing evolution, tracing the vast journey from the first moments of matter to the boundless expanse we inhabit today. As our journey through the birth of the universe comes to a close, allow yourself to sink even deeper into relaxation. Imagine the cosmic hum of ancient light, the echo of the Big Bang stretching across time, and the gentle shaping of galaxies by unseen forces. Feel your thoughts drifting like stars across the sky, your muscles softening as if floating in zero gravity, your breath flowing naturally and effortlessly. Rest here, fully supported in this vast and serene space where beginnings and endless possibilities coexist. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.